In my previous lecture, I started with pulsed electric field assisted extraction, a technique which utilizes electric current as a source to increase the yield of the extraction from different matrices, whether it is a matrix of living cells or of the plant tissues or plant cells. And in that we discussed about the brief historical development of this technique, the mechanism of the technique by which it enhances the extraction efficiency. We also discuss about the instrumentation aspect of this technique, what type of instruments are required, what are the components of the instrument that is involved in this technique. Then we started with the factors that are affecting the extraction efficiency. And in that I told you that there are different factors such as electric field intensity, pulse shape, pulse duration, pulse interval, type of solvent, concentration of solvent and its pH, solvent to feed ratio and temperature, and these were the major factors that can affect the extraction efficiency. So we also discuss in detail about the effect of electric field intensity on the overall extraction yield, and we discussed that as you increase the intensity of the electric current or electric field, the efficiency also increases. But this happens up to a optimal value, and if we further increase the intensity because of the thermal effect, the yield can get decreased because of the thermal degradation of the constituents. And we discussed that the field intensity should be optimum in order to avoid any kind of thermal degradation of the constituents, in order to reduce the power consumption of whole process, and in order to maintain a stable system, because as we increase anything beyond the optimum level, that will have more stress onto the system which is involved in that particular technique. So friends, today I am going to start with the other factors that can affect the efficiency, and first in the list is the shape of the pulse. Again, I will go back to my last day's lecture wherein I discussed that there are different pulse generators depending upon the shape of the pulse that is required. And it has been seen that different pulse shapes have different effect on the extraction efficiency of the technique. And as you can see on the screen, there are different types of pulse shapes which can be used in extraction while using this technique. First one is exponential decay, which is represented in the image A, and you can see this type of waves have initial large value of the electric field which gradually decreases or to a very minimal value. So there is a burst of electric field initially which decreases gradually in case of exponential decay type of pulse shape. Then we have the normal sinus or oscillatory type of pulses of the current, wherein you can see in the figure B the topmost shape of the wave is the sinus wave, which is a normal shape or normal shape of a wave which we generally observe or we generally see. Then we have a square pulse of the current, wherein there is an initial increase in the electric field or the intensity of the current, and that increased intensity is maintained for a specified period of time, and then it decreases to minimal value, and that minimal value is again maintained for a specific period of time. Then again there is an increase or burst in the electric intensity, which is again maintained for a specified period of time. And third type of wave which you can see is the triangular wave, where there is a linear increase in the electric intensity to a particular level which sharply then decreases in a linear fashion, then again it increases. This is a triangular pulse of electric current. So these different types of pulses are used, and by and large if we see then square type of pulses or the oscillatory or the sinus pulses are mainly used in different types of experiment or the extraction experiments. Now on the basis of their mode, these pulses can be monomodic or monopolar or monophasic, or they can be bimodic or bipolar or biphasic. Now it is always considered that bipolar waves are better than the monopolar waves, and you can see in the diagram picture A represents a unipolar or a monopolar pulse of current, whereas the picture B is a bipolar pulse of the current. And we can see that in monopolar we always have a positive flow of the current, whereas in a bipolar mode we have both positive as well as the negative values of the current, and the average value of the pulse is considered to be the electric intensity. And as I told you that bipolars are always considered better than monopolar, because we see that in the image that there is a reciprocating effect that is produced by the bipolar waves. There is an increase in the intensity. That increased intensity in case of square pulses is maintained for a specified period of time. Then that intensity decreases, go below the zero value into negative value, then again it increases. Now this reciprocating electric intensity exposure causes more stress on the cellular membranes, and this enhanced stress is resultant into efficient breakdown or electroporation of the membranes. And once there is an efficient breakdown or electroporation, the overall extraction yield increases. Since these types of bipolar waves they produce lot of stress on the membrane, thereby improving the electroporation, therefore minimum energy or reduced energy is required in case of bipolar pulse electric waves. Then it also reduces the solid deposition on the electrodes. Many times it has been observed that if we are using a monopolar or a unipolar electric current, wherein the intensity is at a constant value irrespective of the shape of the wave we are using, then certain amount of solid start getting deposit on the electrodes, and this sometimes over a longer period of time reduces the efficiency of those electrodes, and a routine maintenance of those electrodes is required, and this solid deposition can be reduced with the help of these bipolar waves. The next factor is the pulse duration. Now pulse duration is nothing but the amount of the time required to get a complete pulse or a complete wave of the electric current. Now if we increase the width of the pulse, that is, we are increasing the duration of the pulse, then better microbial inactivation has been observed, because it has been observed as you increase the width of the pulse, the intensity of the electric field falls into the optimum range, which leads to better microbial inactivation. But again, the pulse width should be in the optimum values, because if we further increase the width of the pulse, the electric field intensity decreases drastically, which will not be able to produce as effective result as they can be produced by the optimum values. And again, it has been observed that if the longer pulses are used, they have a moderate electric field of 100 to 300 volt per centimeter, and these longer pulses have effective pulse electric field extraction efficiency. Now if we go beyond these values or the time of a particular pulse value, then obviously we have to increase the electric field intensity. And once we increase the electric field intensity, we expose the sample to increased electric field intensity for longer duration, there is every possible chance of the thermal degradation. Therefore, I again repeat that the pulse width or the duration of the pulse should always have an optimum value, so that there is we can keep in check the increase in the electric field intensity, thereby keeping into control the thermal degradation of those constituents. But it has further been seen that in order to reach or in order to get the maximum benefit of optimum pulse duration, the maximum transmembrane the pulse duration should be larger than the membrane charging time. Now I'll again go back to my previous lecture, wherein I discuss about different steps that were involved in the electroporation method, and in that the first and the foremost step was the charging of the membrane. So whenever a cell is exposed to a specified amount of current between the electrodes, then the first step is the charging of the membrane. And it has been observed that this charging time can vary from nanoseconds to microseconds. Now, until and unless the cell has undergone this first step, that is membrane charging, it cannot shift on to the second step of electroporation, that is membrane polarization. And therefore, the pulse duration should always be larger than the time required by the membrane to get charged. That is why it is always said that the pulse duration should always be larger than the membrane charging time, because if it is lesser than the membrane charging time, then the membrane will not completely get charged, and once the membrane is not completely charged, membrane polarization will not occur effectively, which will reduce the overall electroporation effect, thereby reducing the extraction efficiency. Next factor is pulse interval, and as the name indicate, it is nothing but the time duration that occur between the two pulses. And the pulse interval, whenever it is increased but to an optimum value, there is always an improved disintegration kinetics of the plant tissues. And when there is improved disintegration, obviously the extraction yield improves. So in simple words, the time duration between the two pulses should have an optimum value in order to get the maximum extraction yield. Because as we discussed that the cell membranes, by virtue of their natural phenomena, they reorient themselves, they will reorient their structure by their own, thereby sealing the pores that are formed with the help of electric pulses. And if we give sufficient time between the two pulses to come in contact with the cells may reseal and the pores will reseal, thereby decreasing the extraction efficiency, and therefore the pulse interval should always be optimum. Next factor is the effect of solvent, its concentration and pH on the extraction efficiency. I'll go back to one of my lectures where we discuss about the fundamentals of extraction, wherein we discussed that the solubility or the extraction also depends upon the characters of a solvent, and the characters of the solvent can be defined in terms of polarity and solubilizing power. And when we talk about the pulse electric field assisted extraction, another factor comes into play, that is the conductivity ability of the solvent. So in short, there are three major factors that will govern the solvent characters in case of pulse electric field assisted extraction. Number one is the conductivity of the solvent, second is the polarity, and third is the solubilizing power of the solvent. And it has been observed that the solvents which are having high conductivity, they exhibit increased electroporation, because lesser will be the resistance provided to the electric current to flow through the solvent because of their high conductivity, and once less resistance is there, the electroporation increases, which increases the overall extraction yield of the process. Further, if a solvent is having high solubilizing power, then obviously it will have a direct effect on the mass transfer rate. Solvents with low solubility power will have low mass transfer. Solvents having high solubilizing power, they will have high mass transfer rate, and as the mass transfer rate increases, there is an increase in overall yield of the extraction process. Therefore, high solubilizing power solvents, they will have a positive effect on the extraction yield. Then we know that the secondary metabolites, they have varied chemistry, they have varied chemical structures, and by virtue of varied chemistry, they have different varied chemical properties, and therefore these secondary metabolites behave differently at different pH values. And this behavior of different solute molecules with respect to pH can be directly correlated with their extraction efficiency of a process. Say for example, Terhellos, when it was extracted from the beer waste of a brewing yeast, it was found that the Terhellos yield was significantly increased as the pH of the media was increased from 3 to 7. And it's not only the pH of the solvent that affects the extraction yield, it is the strength of the solvent that also affects the extraction efficiency. We know that secondary metabolites have different chemical properties, varied chemical properties. Therefore, some of the chemical constituents or secondary metabolites, they are soluble in organic solvents, whereas more polar secondary metabolites, they always prefer aqueous media to get solubilized. Whereas in between the chemical constituents or secondary metabolites having polarity in between, they may require combination or a combination of an organic and the aqueous phase. So therefore, solvent strength has a significant impact, and there was a study wherein chondroitin was extracted from a given sample, and it was found that yield of extracted chondroitin was increased significantly when the strength of sodium hydroxide solution was increased up to 3%. And beyond this strength, there was no significant increase in the chondroitin yield that was found in that particular experiment. So we can say that chondroitin yield can be increased up to 3% of sodium solution when it is used as an extraction solvent. Another factor that can affect the efficiency of this technique is solvent to feed ratio. And in order to get better yield, in order to make your process economical, the ratio of solvent to the feed should always be optimum. If we talk about general principle, then yes, the yield of the extraction increases with the increase in the solvent to feed ratio, but again up to a specific value. And beyond that value, either there will be no significant increase in the yield, one. Second, beyond that specific value, the process may become uneconomical, because a lot of energy then will be required to evaporate that solvent, large amount of solvent, and thus the process may become uneconomical, and the solvent cost will also add up to the overall cost of the process. And the third point is that the concentration of the solute in the final solution will decrease, because we are increasing the amount of solvent to extract out the same amount of the drug which was extracted previously for smaller amount with the smaller amount of solvent. The final solutions which we will get, the sample in which we have used large amount of solvent, large volume of solvent, then obviously the solute concentration in that particular volume will be less in comparison to the extract which we obtained by using less volume of the solvent. But again, bottom line is, if we are not using the optimum solvent to feed ratio, that will have detrimental effect on the extraction yield. This was just in case we are increasing the solvent to feed ratio. Now there is another scenario wherein we decrease the solvent to feed ratio. Say for example, we have to extract out 1 or 2 gram of drug, and when we increase the solvent to feed ratio, we extracted that 1 gram of drug with say 50 ml of solvent. But in the second scenario, we are extracting 1 gram of drug say with 10 ml of the solvent. So we are reducing the point of contact between the solvent and the drug, because now we are using lesser volume of the solvent. In such cases, solvent may easily get saturated, thereby decreasing the extraction yield, and this saturation will also have the effect on the mass transfer rate. So in either of the scenarios, we have to optimize the solvent to feed ratio in terms of the economical viability of the process, in terms of the maximum solubilization of the solute molecules in the given volume of the solvent, and third, in order to get the appropriate concentration of the final extract in terms of the amount of the solute that is present in that particular extract. And last but not the least factor is of temperature. And again, I'll go back to one of my lectures wherein we discuss the fundamentals of the extraction process, wherein we discuss as we increase the temperature, there is an increase in the yield because the viscosity of the solvent decreases. When the viscosity decreases, it enhances the penetration of the solvent into the matrix, and as the penetration enhances, the solvent comes in direct contact with the solute, and by virtue of the increased temperature, the solubilizing power of the solvent also increases. Thereby, the net effect is the extraction yield increases. But again, if you increase the temperature beyond the optimum values, again I will repeat that all these parameters, they have to be optimized, because all these parameters will vary from sample to sample. So if we increase the temperature beyond the optimized values, then there is every possible chance of thermal degradation of the constituents, which will eventually cause decrease in the overall extraction yield. Now we move on to the last part of the pulse electric field assisted extraction, and that is the application of this technique. Now, since we are discussing about the extraction techniques, first and foremost application of this technique is in the extraction of cellular components. The cells can be of animal cell or the plant tissues or the plant cells. Then preservation of food items. We know that by virtue of when we discuss the historical background of this technique, we discussed that this technique was initially used for increasing the shelf life of the food items, and therefore the second and the most important application is the preservation of food items. Third is drying. Fourth is enzymatic activity modification. And this is important because it has been observed that certain food items, they get degraded by a specific enzymatic activity, or their organoleptic characters changes by those enzymatic activities, and by using pulse electric field we can reduce those enzymatic activity, thereby preserving the organoleptic characters of those food items. Then another commercially important application of this technique is the wastewater treatment. Now we will discuss each and every aspect. So coming on first to extraction, as I told you that pulse electric field has shown an improved extraction yield over various other modern as well as conventional techniques. And if this technique is used in combination with the pressing, as you can see in the figure, there has been significant increase in the yield of the product that has to be obtained from the material when pulse electric field technique is used in combination with the pressing. Now it has also been observed that some of the conventional and modern methods have various limitations, like long extraction time, low extraction yield, high consumption of solvent, high extraction temperature, which always have a risk of thermal degradation, and all these limitations can be overcome by using pulse electric field assisted extraction. Now this technique has been used to extract secondary metabolites from almost every part of the plant, and it's not only the part of the plant, but various agro-industrial waste have also been used to extract out the remnants of the desirable secondary metabolites from those waste products. It has also been used to extract out pigments, various types of proteins, and even if you want to extract out enzyme from a particular microorganism, this technique can be used. Now if you look into this table, I have taken certain examples where in different secondary metabolites a comparison of the extraction yield of various secondary metabolites has been made. So in this example I have wherein polysaccharides were extracted from frog by using pulse electric field assisted extraction, maceration and EAE, that is enzymatic assisted extraction. And you can see that PF was done for only 4 minutes, maceration was done for 2 hours, and enzyme assisted extraction was done for 5 hours. And there was a significant difference in the yield of polysaccharides that were obtained by using pulse electric field. Similar results were observed when the sample corn was used to extract out polysaccharides, and a comparison was made in case of microwave assisted extraction and pulse electric field assisted extraction. And as you can see that when microwave was used to extract out polysaccharides from the corn, only the yield was 6.2% when the extraction was carried out for 33 minutes, almost half an hour. Whereas in case of pulse electric field, the extraction was carried out only for 4 minutes with the increased yield of around 7%. These are the other examples. You can see that terhalos, which was extracted from the bare waste, and a comparison was done between pulse electric field assisted extraction, ultrasound assisted extraction, and microwave assisted extraction. And you can see there was, though the yield in microwave assisted extraction was much higher in comparison to pulse electric field assisted extraction, but if we compare in terms of time, then yes, pulse electric field assisted extraction took very short time in order to extract around 3% of the terhalos. Similarly, polyphenolic compounds, when isolated using different techniques, similar kind of results were obtained. The yield in pulse electric field assisted extraction was much higher in comparison to ultrasound assisted extraction and microwave assisted extraction. Next application is in terms of preservation of food items, and as we have already discussed that pulse electric field assisted technique is largely used to increase the shelf life of the food items. It not only kills the microorganism, thereby retaining the original composition of the food item, thereby retaining the original organoleptic characters of the food item. It also helps in reducing the change in the organoleptic character that can be produced by certain enzymes over the period of time. So by using this technique, we can deactivate those enzymes also, thereby again preserving the organoleptic character of those particular food items. Drying is another application wherein this technique is used to remove certain percentage of water before the material is exposed to the further drying. And it has been observed that by following this method, there is a significant improvement in the quality of the food product that is obtained by drying using PEF technique and by osmotic drying. And last major application is the wastewater treatment, and a study was done in case of hospital wastewater wherein that wastewater was treated with PEF, and it was found that by treating the water with PEF, there was significant decrease in the concentration of living bacteria because Propedium monoxide was added, and this agent basically binds to the DNA of the bacteria, thereby inhibiting its amplification in PCR. So in order to differentiate between living and dead bacteria, this study was done, and there was significant decrease in the concentration of the living bacteria, and thus one can easily conclude that pulse electric field technique is a very good alternative to the chemical disinfectants that are used for wastewater treatment. So friends, this was all about the pulse electric field assisted extraction, and in my next lecture I will start with another extraction technique, that is supercritical fluid extraction. Thank you.